Hello! Today we're going to dive into some incredibly useful tools for solving triangles that aren't right-angled. By the end of this video, you will be able to: first, apply the law of sines to find unknown sides and angles. Second, apply the law of cosines to find unknown sides and angles. And third, you'll be able to identify and solve for ambiguous cases in the law of sines. Think of these laws as your go-to strategies when the Pythagorean theorem and SOH-CAH-TOA just won't cut it. Let's get started with the law of sines. Our first tool is the law of sines. It's a powerful relationship that connects the sides of any triangle to the sines of its opposite angles. Let's consider a triangle with angles A, B, and C, and the sides opposite them, which we'll call A, B, and C. The law of sines states that the ratio of a side to the sine of its opposite angle is constant for all three sides of the triangle. In other words, A over sine A equals B over sine B equals C over sine C. This means that if you know a side and its opposite angle, you can find any other side or angle in the triangle, provided you have one more piece of information. So when should you use the law of sines? It's perfect for two main scenarios. First, when you have an angle-angle side, or AAS, triangle. This means you know two angles and the side that is not between them. Second, when you have an angle-side angle, or ASA, triangle. Here you know two angles and the side that is between them. In both of these cases, you'll always have a complete pair, a side and its opposite angle, to start with. Let's see it in action. Let's work through our first example. We'll solve an AAS triangle. Imagine a triangle where angle A is 30 degrees, angle B is 45 degrees, and the side opposite angle A, side A, is 10 units long. Our goal is to find the remaining angle, C, and the remaining sides, B and C. First, let's find angle C. We know that the angles in any triangle add up to 180 degrees. So angle C is 180 degrees minus the sum of angles A and B. That's 180 minus 30 plus 45, which gives us 105 degrees. We found our first unknown. Now, let's find side B using the law of sines. We'll set up a proportion using the known pair, A, and the pair we want to find, B and B. The equation is A over sine A equals B over sine B. Plugging in our values, we get 10 over sine of 30 degrees equals B over sine of 45 degrees. To solve for B, we can cross-multiply, or simply multiply both sides by sine of 45 degrees. This gives us B equals 10 times sine of 45 degrees, all divided by sine of 30 degrees. Using a calculator, we find that B is approximately 14.14 units. Finally, let's find side circa. We'll use the same process, but this time with angle C. We set up the proportion A over sine A equals C over sine C. That's 10 over sine of 30 degrees equals C over sine of 105 degrees. Solving for C, we get C equals 10 times sine of 105 degrees divided by sine of 30 degrees. This gives us approximately 19.32 units. And just like that, we've solved the entire triangle. Now for the part that can be a bit tricky, the ambiguous case of the law of sines. This happens when you're given a side-side angle, or SSA, triangle. In an SSA triangle, you know two sides and an angle that is not between them. The problem is, this information doesn't always define a unique triangle. There might be two possible triangles, one triangle or even no triangle at all. Let's visualize this. Suppose we know side A, side B, and angle A. We can draw angle A and side B. Now, side A is opposite angle A. We can swing side A from the end of side B. Depending on its length, it might not reach the other side of the angle, it might just touch it, or it might cross it in two places. This is why it's ambiguous. So how do we handle this? We start by trying to find the first unknown angle, let's say angle B, using the law of sinus. We set up the equation A over sine A equals B over sine B. Rearranging to solve for sine B, we get sine B equals B times sine A, all divided by A. The value we get for sine AB tells us everything. Let's look at the three possible outcomes. First, if the value of sine B is greater than 1, there is no triangle. Remember, the sine of any angle can never be greater than 1. So if your calculation gives you a value like 1.2, you know there's no solution. Second, if the value of sine B is exactly 1, there is one triangle. This happens when side A is exactly the right length to form a right-angled triangle. Third, and this is the ambiguous case, if the value of sine B is between 0 and 1, there are two possible triangles. This is because there are two angles between 0 and 180 degrees that have the same sine value. One is acute and the other is obtuse. Let's walk through an example of this ambiguous case. Let's tackle an ambiguous case example. We'll solve an SSA triangle that has two solutions. Consider a triangle where angle A is 30 degrees, side A is 7 units, and side B is 10 units. Notice we have two sides and an angle not between them, so we're in the SSA case. Our first step is to find angle B using the law of sines. We set up the proportion A over sine A equals B over sine B. Plugging in our values, we get 7 over sine of 30 degrees equals 10 over sine B. Solving for sine B, we get sine B equals 10 times sine of 30 degrees divided by 7. This simplifies to 10 times 0.5 divided by 7, which is 5/7. Since 5/7 is between 0 and 1, we know there are two possible triangles. Let's find the two possible values for angle B. The first angle, B1, is the inverse sine of 5/7, which is approximately 45.58 degrees. The second angle, B2, is 180 degrees minus B1, which is approximately 134.42 degrees. We now have two possible triangles to solve. Let's solve for the first triangle, using B1. For triangle 1, angle A is 30 degrees, and angle B1 is 45.58 degrees. Angle C1 is 180 minus their sum, which is 104.42 degrees. Then, we use the law of sines to find side C1, which comes out to approximately 13.54 units. Now for the second triangle, using B2. For triangle 2, angle A is 30 degrees, and angle B2 is 134.42 degrees. Angle 2 is 180 minus their sum, which is 15.58 degrees. We then find side C2, which is approximately 3.64 units. And there you have it. Two complete valid triangles from the same initial information. Now, let's look at a no-solution scenario. This is another outcome of the SSA case. Consider a triangle where angle A is 30 degrees, side A is 4 units, and side B is 10 units. Again, we have an SSA triangle. Just like before, we'll start by trying to find angle B using the law of sines. We set up the proportion A over sine A equals B over sine B. Plugging in our values, we get 4 over sine of 30 degrees equals 10 over sine B. Solving for sine B, we get sine B equals 10 times sine of 30 degrees divided by 4. This simplifies to 10 times 0.5 divided by 4, which is 5/4, or 1.25. And here's our answer. The value we found for sine B is 1.25. But remember, the sine of any angle must be between -1 and 1. It can never be greater than 1. Since sine B is greater than 1, there is no angle B that satisfies this condition. Therefore, no triangle can be formed with these dimensions. The answer is simply no solution. This is why it's so important to check the value of the sine function when you're in the SSA case. It's your first clue to whether a solution exists at all. Now let's move on to our second major tool, the law of cosines. This law is a generalization of the Pythagorean theorem and is used when the law of sines won't work. The law of cosines has 3 forms, one for each side. They all follow the same pattern. For example, a squared equals b squared plus c squared minus 2 times b times c times the cosine of angle A. Notice that if angle A were 90 degrees, cosine of A would be 0, and the equation would simplify to a squared equals b squared plus c squared, the Pythagorean theorem. So it's a more general rule. When should you use the law of cosines? It's for the two cases where you don't have a complete side angle pair. First, when you have a side-angle side, or SAS, triangle. This means you know two sides and the angle between them. Second, when you have a side-side-side, or SSS triangle. This means you know all three sides. In both of these situations, you can't use the law of sines to start, so the law of cosines is your first step. Let's see an SAS example. Let's solve a triangle using the law of cosines. We'll start with an SAS case. Suppose we have a triangle where side A is 10 units, side B is 12 units, and the angle between them, angle C, is 70 degrees. Our goal is to find side C and angles A and B. Since we have two sides and the included angle, we use the law of cosines to find the third side, C. We use the form C squared equals A squared plus B squared minus 2AB cosine C. Plugging in our values, we get C squared equals 10 squared plus 12 squared minus 2 times 10 times 12 times the cosine of 70 degrees. Calculating this, we get C squared equals 100 plus 144 minus 240 times, approximately 0.342. This gives us C squared equals 161.92. Taking the square root, we find that side C is approximately 12.73 units. Now that we know all three sides, we can find the angles. We can use the law of cosines again, or we can switch to the law of sines, which is often simpler. Let's find angle A using the law of sines. We set up the proportion A over sine A equals C over sine C. That's 10 over sine A equals 12.7, 3 over sine of 70 degrees. Solving for sine A, we get sine A equals 10 times sine of 70 degrees, divided by 12.73. This gives us approximately 0.738. Taking the inverse sine, we find that angle A is approximately 47.58 degrees. Finally, we can find angle B by subtracting the other two angles from 180. Angle B is 180 minus 70 minus 47.58, which is approximately 62.42 degrees, and our triangle is solved. Let's do one more example, this time an SSS triangle. Here, we know all three sides and need to find all three angles. Suppose we have a triangle with side A equals 5, side B equals 8, and side C equals 11. We need to find angles A, B, and C. Since we don't have any angles, we must start with the law of cosines. Let's find angle A first. We use the form A squared equals B squared plus C squared minus 2 BC cosine A. We need to rearrange this to solve for cosine A. After some algebra, we get cosine A equals B squared plus C squared minus A squared, all divided by 2 BC. Plugging in our values, we get cosine A equals 8 squared plus 11 squared minus 5 squared, divided by 2 times 8 times 11. This simplifies to 64 plus 121 minus 25 divided by 176. That's 160 divided by 176, which is approximately 0.909. Taking the inverse cosine, we find that angle A is approximately 24.62 degrees. Now let's find angle B. We can use the law of cosines again, or the law of sines. Let's use the law of sines this time. We set up the proportion A over sine A equals B over sine B. That's 5 over sine of 24.62 degrees equals 8 over sine B. Solving for sine B, we get sine B equals 8 times sine of 24.62 degrees divided by 5. This gives us approximately 0.667. Taking the inverse sine, we find that angle B is approximately 41.81 degrees. Finally, we find angle C by subtracting the other two from 180. Angle C is 180 minus 24.62 minus 41.81, which is approximately 113.57 degrees. Notice that this angle is obtuse. The law of cosines correctly gave us an acute angle for A, and the law of sines gave us an acute angle for B. The largest angle, C, is opposite the largest side, C, which is a good check. Let's quickly recap what we've learned today. We've covered two essential tools for solving non-right triangles. First, the law of sines, which is used for AAS ASA, and SSA triangles. Remember to be very careful with the SSA case, as it can lead to two triangles, one triangle, or no triangle at all. Second, the law of cosines, which is used for SAS and SSS triangles, is a more general form of the Pythagorean theorem and is your starting point when you don't have a side angle pair. The key is to identify which case you have based on the information given. Once you know that, you know which law to apply first. After that, you can often switch to the law of sines to find the remaining parts, as it's usually less calculation intensive. You are now equipped to solve a wide variety of triangle problems. Keep practicing and you'll master these concepts in no time. Thanks for watching.